We've looked a little bit at the history of the search for life on Mars. It's worth now looking in a little bit more detail about Mars as a location for life. We've seen what makes a planet habitable. It includes a source of liquid water, a source of energy, a source of elements and other nutrients, and physical conditions suitable for life. Let's look at each one of these and see how Mars matches up to those requirements. First of all, water on Mars. Well, today Mars has a desiccated surface. In fact, there are many images, such as this one, sent back by Mars rovers, showing this dry, desiccated surface. There's no liquid water on the surface of Mars. The atmospheric pressure is too low for standing bodies of liquid water to persist for any length of time. But the evidence is that this wasn't the case in the Martian past. Indeed, as early as the Viking orbiters, images were sent back of valley networks and catastrophic outflow channels dating back many billions of years, the early history of Mars, that suggests that early Mars had a lot more liquid water than today. This is a rather beautiful image of Jezero crater in the northern hemisphere of Mars, showing what looks like a river flowing into an asteroid crater. It's a false colour image. Some of these colours correspond to minerals such as olivine and pyroxene found in volcanic rocks, and some of these colours correspond to clays, alteration products caused by volcanic rock reacting with liquid water. We can also see here a feature that looks very much like a delta. All of these features found in different places on Mars suggest that in the early history of Mars there was much more liquid water than there is today. We think that Mars essentially had three epochs. The early epoch in the Noachian was when there was abundant liquid water, and this would have been reacting with volcanic rock, creating environments with essentially a neutral pH in which clays were being produced. And then, as Mars began to dry up later in its history, there was interactions between sulfur dioxide produced in volcanoes and liquid water, producing acidic waters. And Mars went through a phase where many of its water bodies may have been more acidic than in its very early history. And then in the third epoch, very broadly, Mars transitions into what we observe today, a very dry environment, no standing bodies of liquid water, and probably liquid water interactions confined to the deep subsurface, if it even occurs there. There is some evidence, though, for liquid water in the near-surface environment even today. These are images of what seem to be brine channels seeping out from the subsurface of Mars, reported only 2 years ago, that suggest that underneath the surface conditions may be suitable for the formation of brines that might seep out around the edges of impact craters and other features onto the surface of Mars. So it's possible that even in the subsurface of Mars there is liquid water. But if we think more broadly about the habitability of a planet, we can certainly say that in the early history of Mars there was more liquid water than today. So at least in terms of the requirement for liquid water in order to sustain life, early Mars would have been habitable. What about elements and nutrients for life? In an earlier lecture, we saw how life needed 6 key elements. Let's have a look at those in turn. First of all, carbon. Well, we know there's a source of carbon. There's carbon dioxide in the atmosphere. There's just over 95% carbon dioxide in the Martian atmosphere, and we know there are microbes that can use carbon dioxide as a source of carbon to fix carbon. So that doesn't seem to be a problem. There's hydrogen available, either in liquid water, maybe even present today, but certainly in ice, and some of that ice may have melted in the past. If we think about the early history of Mars, there was certainly liquid water to provide a source of hydrogen. What about nitrogen? Well, nitrogen is the big unknown, and we don't know whether there are sources of fixed nitrogen on the surface of Mars that could supply nitrogen for biology. Indeed, the Mars Science Laboratory might give us greater insights into whether there's nitrogen and where it might be distributed. Nitrogen could be one of the big problems for Martian life. There's oxygen available on Mars, a very little bit in the atmosphere, 0.14% in the atmosphere, but there are oxygen atoms in water and in other compounds. So there seems to be an accessible supply of oxygen atoms, at least, to supply the oxygen requirement for life. What about phosphorus? Well, we know that there's phosphorus in apatite. These are phosphate-containing minerals found commonly in volcanic rocks on the Earth, but also known to exist on Mars. So we know there's a source of phosphorus, and we also know there's sulfur. Sulfates have been found on Mars, such as magnesium sulfate, and these salts could plausibly supply sulfur to life on Mars. So the 6 elements for life, CHNOPS, seem to be available apart from possibly nitrogen. And finding the nitrogen on Mars is one of the key challenges for astrobiologists if we're to show that Mars is habitable with respect to the basic elements required for life. Of course, there are many other elements on Mars as well: magnesium, calcium, iron, potassium and sodium that are found in volcanic rocks, and these could be used by life for different chemical reactions and in different pathways for biochemistry as they are on the Earth. One problem for Mars is geochemical turnover. How do we recreate these energy supplies that life needs? Unlike the Earth, Mars does not have plate tectonics today. There's some evidence for ancient magnetic fields that have essentially been trapped in rocks when they were liquid in the early history of Mars and then solidified, preserving a remnant of the Martian magnetic field. But those plate tectonics have long since stopped, and so one wonders how you would get geochemical turnover, how you would get new energy and nutrient supplies turned over to provide these requirements for life. Well, one way could be volcanoes. Mars does seem to have active volcanism in its recent history. Volcanoes may have melted rock, stirred up energy and nutrients, and provided the disequilibria, the chemical conditions in the surface that would have provided energy for life. So there are ways in which we could get geochemical turnover required to provide new energy and nutrient supplies for life. What about the physical conditions on Mars? Well, we've already seen how the surface is very extreme. High levels of ultraviolet radiation. There's no ozone shield on Mars. If you went sunbathing on Mars, you would get sunburnt about 1,000 times faster than you would be on the surface of the Earth. This is a very damaging environment for life. It's very desiccating, no liquid water on the surface of Mars. High ionizing radiation as well. These are high energy particles from the Sun and the galaxy that bombard the surface of Mars and its near surface environment and make conditions very challenging, particularly as there's no liquid water for any potential biology to repair its biochemical processes. And as we saw in the Viking biology experiments, there may be oxidants in the soils. There's certainly perchlorate, and these compounds could provide a challenge for life living on the surface. But this may not be the same in the subsurface of Mars. The ultraviolet radiation is cut out, the ionizing radiation is reduced from the rocks, and there might be liquid water, maybe even brines in the subsurface of Mars, providing habitats for life. That's the story of present-day Mars, but as we've already seen, the physical conditions for life on the early history of Mars were very different, and certainly, given that there was liquid water on the surface of the planet, it seems that the physical conditions on the surface may have been more conducive to life. Where would we look for this life on Mars? Well, today we would probably have to go into the deep subsurface. The surface of Mars does not look like a very good place for life to be thriving. But in the subsurface, maybe we could drill beneath the surface, beneath that layer of oxidants in the soil, and perhaps reach pockets on the subsurface of Mars where there might be liquid water and habitats for life. So it seems that the search for present-day life on Mars might best be accomplished by looking in the deep subsurface. What about past life? Well, if liquid water was abundant on the surface of Mars in the past, all we have to do is go to ancient sediments laid down in the ancient surface of Mars and see whether there are remnants of life there. This is an image of Mount Sharp taken by the Mars Science Laboratory. And this rover will explore some of these minerals. You can see an image here, and these white dots show what's called an unconformity. Above the white dots, you can see a lava layer that's been laid down on top of ancient sediments. And below those white dots, sediments that may contain clays, sulfates and other minerals associated with the interaction of water with volcanic rocks and the production of different minerals. The Mars Science Laboratory will explore these ancient minerals to see whether they might contain ancient organic compounds, whether they might be places that were habitable for life. And one of the instruments with which it will do this is the Sample Analysis at Mars package, the SAM instrument shown here, that will sample these materials in the future and see whether they contain any organic materials that might be of interest for assessing Mars as a habitable world. What might we look for on Mars? Well, we might look for the same things that we saw in an earlier lecture that we look for to show evidence for life on early Earth. We might look for shapes of fossils that resemble life. We might look for the organic remains of living things that have long since been buried and died. And we might also look for chemical signatures of life or chemical changes caused by life, such as isotopic fractionation, or maybe even changes to minerals that are distinctive for biology. And all of these lines of evidence might help us to determine whether early Mars ever had life. What would be the implications if we found no life on Mars? Many people think that we're going to Mars to search for life, and we really want to find it. And if astrobiologists didn't find life on Mars, we would be deeply disappointed. But in fact, a lack of life on Mars would be a very, very significant finding. What would it mean? Well, it might mean that something was missing on the surface of Mars. We've seen how we don't know about the distribution of nitrogen on the surface or subsurface of Mars. Maybe that's missing. Maybe that prevents life from having taken hold on Mars. It might be something to do with the origin of life. If the origin of life is extremely rare and requires very specific conditions, maybe it occurred on the Earth and did not occur on Mars. It might also be that there are habitats on Mars that are uninhabited. Perhaps they're uninhabited because there was no origin of life on Mars, or these habitats are not connected with environments on Mars that do contain life. Uninhabited habitats are habitats that contain all the ingredients for life, all the requirements for habitability, but there's no life there. It might be that we will find that we are exploring uninhabited habitats on Mars, and yet it could be that other regions of Mars are inhabited. So all of these problems may lead to a lack of a discovery of life on Mars, and in order to find out why Mars did not have life, we would have to know more about the origin of life and more about the way in which life can persist on planetary surfaces over billions of years. It is intriguing, though, that when Earth had life in its early history, Mars had liquid water. And so the question is, if Mars had no life, what was different about Mars compared to the Earth, despite the fact that both planets seem to have been quite similar in their early history? The search for life on Mars also has implications for policy. This is an area of policy called planetary protection that's been developed by the Committee on Space Research. And planetary protection is concerned really with two problems. First of all, back contamination. That's where we bring materials back to the Earth, and there's a possible, if somewhat unlikely, threat of contaminating the Earth with some extraterrestrial organism. This is actually an image of the Apollo 11 astronauts being quarantined on their return from the Moon. The likelihood of contaminating the Earth with some extraterrestrial organism is very low, but out of prudence, planetary protection regulations address this potential problem. Another challenge addressed by planetary protection is forward contamination, and that's the contamination of planets that have life with Earth microorganisms. And this is much more of a concern for Mars. If Mars has life, should we contaminate the planet, and how can we go about preventing the contamination of the planet by cleaning up spacecraft, for example, before we send them there? This is an image of the Viking landers in their heat shields. They were literally cooked like turkeys in a giant oven before they were sent to Mars to kill microorganisms on their surfaces, essentially sterilize them. These are the sorts of protocols that can be used to clean up spacecraft before they're sent to Mars. Nowadays, different protocols are used because of the sensitivity of modern electronics. But planetary protection has become a very serious concern in the exploration of Mars and the possibility that it may have habitable environments for life. Planetary protection essentially splits missions into different categories. For example, Category 1 is a mission where there's no direct interest for understanding the origin of life, and this might be a completely desiccated asteroid where there's really no chance of contaminating some sort of indigenous biosphere on that asteroid. And it goes right the way through to Category 5, which is returning samples to Earth, where there may be a concern about back contamination, bringing biological entities from a planet such as Mars to the Earth, and the precautions that should be taken to ensure that those samples are properly handled and properly investigated before they're released for wider investigation. So what have we learned in this lecture? Well, hopefully we've learned that Mars had much more liquid water in its past. It may even have liquid water today in the form of brines. It seems to have many of the elements and nutrients required for life to exist, but we don't know the global distribution of these, particularly crucial elements like nitrogen. Mars lacks plate tectonics, and so the regeneration of energy sources and nutrients in the crust could be a problem for life, although geochemical turnover might be caused by volcanoes. And we've also learned that the search for life on Mars has policy implications, particularly for planetary protection, which provides guidelines for prudent safeguards for exploring Mars and preventing contamination.